Can you prove that there's no life in the universe? Can we be sure that an asteroid is going to hit us in the future? And why is Jupiter so radioactive? All this and more in this week's Question Show. Welcome to the Question Show. Your questions, my answers. As always, wherever you are across my channel, if a question pops in your brain, just write it down. I will gather them up and I will answer them here. All right, let's get into the questions. Tony Wells 6990. You can never prove that there is no other life in the universe. Obviously, you've probably heard the saying that you can't prove a negative. So, you can't prove that we are alone in the universe. All you can do is search for life in the universe and fail to find evidence in a more comprehensive manner in a widening sphere around yourself. And if you assume that we don't live in a special part of the universe, that the amount of life that we find around Earth is roughly the amount of life that we will find in other parts of the universe, then as we explore farther and farther and we find no life, then we can sort of assume with increasing probability that the rest of the universe is empty. Or if we find one planet with life every 10 light years, then we can assume that that number will hold throughout the entire universe. Now, obviously, there are specific things like whether or not you're in the galactic habitable zone, whether or not your galaxy has lots of star formation in it, whether it had interactions with supermassive black holes. There will be modifications on it. But you can never know. There could be some little corner of the universe far, far away where life is hiding out. And totally, 100%. But, if we search for thousands of years and we never find one life form anywhere, and we've expanded, our civilization is now on 1,000 worlds and we've never seen anything ever, then at a certain point we can sort of safe to say we're alone in the universe. And there's like some practical work that's being done in this area. One example, and this was sort of originally for the LUVOIR telescope, the Large Ultraviolet Infrared Observatory, which was going to be the successor to the Hubble Space Telescope. And there was going to be a 8-meter flavor and a 15-meter flavor. Like, imagine a telescope that is 15 meters across. Like, it is to James Webb what James Webb is to Hubble. Like, James Webb is about 50 times more sensitive than the Hubble Space Telescope. And so LUVOIR would be about 50 times more sensitive than James Webb. And one of the things that it could potentially do is detect biosignatures in the atmospheres of other planets. Like, once astronomers finally stop arguing, they've decided what is the proper biosignature, and it could detect it in such a radius around us. Like, if you don't see any life within the radius that LUVOIR could detect, then you could say with like 95% probability that we are alone in the universe. And then the next telescope comes out and maybe it has 50 times the resolution of LUVOIR, and then it would tell you that we are 98% likely to be alone in the universe. And so you'll never hit 100%, but if you're at like 98%, 99%, that seems pretty alone to me. Now, you probably noticed the Star Trek planet name that's appeared above my shoulder. If you haven't, they'll be back. Don't worry. And this is a way for you to vote, for you to tell us what you thought was the best question of the week. And so when we added up all the votes from last week, the answer we got was from Noor Ahmed. How has information about space research become more truthful or more muddied than it was in the past? And I guess that gave me a chance to talk about what I'm specialized in, which is space science communication, which was a lot of fun. So thanks for the question. Thanks everybody who voted. So remember, you're going to see the planet names come up at the end of the episode. Write down the planet that you think was the best question, best answer. We'll tally them up and we'll celebrate it next week. Mantis Scatlaris 8261. Can scientists be full 100% sure if a certain asteroid will hit the Earth in the future, as they do in the movies, or is there always a small possibility that collision will just be a near miss? Astronomers tend not to work in certainties. And so when they detect an asteroid that has a orbit that will cross the Earth's orbit at the same time that the Earth is there, then they assign a probability. And in fact, astronomers have a scale that they use. It used to be called the Torino scale. Now I think it's called the Paloma scale. And with 10 on the scale being there is a 100% certainty that an asteroid is going to, or I think it's like, they never go to 100, I think it's like 90% certainty that there will be a large asteroid that's going to hit the Earth and cause damage at a global level. And then they scale that down where you can have a slight chance of a not very dangerous asteroid hitting us in the future. And so various asteroids will find their way onto the scale. And right now there are no asteroids on that scale, but at various times asteroids like Apophis have gotten a slot on the scale. And then with more observations, astronomers are able to rule it out. And it's that needing more observations, right? It's that requirement that you pin down the location and the future movements of that asteroid with more and more certainty and accuracy. And the way it usually works out is an asteroid is found, astronomers do rough calculations, they realize that the asteroid has a chance to be kind of in the danger zone, and then they request time on other telescopes, more powerful telescopes, they do follow-on observations, they're able to trace and sort of specifically figure out what the future trajectory of that asteroid is. So we can never be 100 certain, but at a certain point, the zone of uncertainty for the asteroid encompasses the entire planet. And so at a certain point, a few years into the future, you will know that yes, with certainty, that asteroid is going to hit the planet. And in fact, astronomers have gotten so good now that they are detecting asteroids on collision courses with Earth hours, days before the collision happens. They're able to know exactly when and where the asteroid is going to hit, and then people know to go out and watch for it. And so we recently just got one in Germany where astronomers predicted, actually it's like one astronomer in Romania who is just crushing it. He's been finding all of these asteroids a few hours before they hit, and then all these other astronomers jump on their telescopes, they confirm the location and pin down. And so this whole prediction process is getting much, much better. With asteroids that are small, that are about to hit us in just a few hours or a few days, they're still working on being able to sort of push that back. And there are new telescopes and observatories that are coming online in the coming years that will do an incredible job of measuring as many asteroids as possible. So we don't know if an asteroid is going to hit us with a 100% chance, but at a certain point, the probability gets big enough that you start to say, should we send a DART-like mission to try and push it off its trajectory into something that's safer? But we do know with 100% certainty that asteroids are going to hit us. So when you think about the sizes of asteroids out there, like imagine like a 10-meter asteroid, the kind of thing that blew up over Tunguska in 1908. They can cause pretty significant damage on the ground. It blew down forests for thousands of square kilometers. Fortunately, nobody was there, but if it hit a city, it would be like a nuclear weapon dropping on a city. They hit us about once every 1,000 years, and that's a 100-meter asteroid. Smaller asteroids, like 10-meter asteroids, when you think about the one that exploded in the sky above Cheleb in Russia, those happen about every 10 years. So we know that 10-meter asteroids, and generally they hit the ocean, like we don't even see them, but every 10 years or so something explodes that is detectable. And then you've got the biggest ones, the 1,000-meter asteroids, kilometer across, and they can cause just wholesale destruction on a hemisphere of planet Earth. They're not as big as the one that killed the dinosaurs, but they're still a very bad day for a lot of people. And a few of those hit us every million years. And so if you run the clock for a million years, at the end of your million years, there will have been a couple of 1,000-meter asteroids that hit the Earth. If you run the clock for 1,000 years, you'll have gotten one 100-meter asteroid, a city killer. And if you run the clock for 10 years, you will have ended up with one 10-meter asteroid. And it's just a probabilities out there. David Guy 209, why is Jupiter so radioactive? When NASA sends spacecraft to Jupiter, they have to remember that there is this giant magnetosphere that surrounds the planet. And that is filled with particles that are high speed trapped from the sun. And they are just orbiting around Jupiter like a kind of a whirling, dangerous, radioactive buzzsaw. And we have that here on Earth. I mean, have you ever heard of the Van Allen belts? We have a magnetosphere around the Earth, and a portion of the magnetosphere is just holding these charged particles that are moving at intense speeds that were captured from the sun and space, and they're just whirling around the planet, following the magnetic fields of the Earth, like a giant particle accelerator that surrounds planet Earth. And there is one around Jupiter. Jupiter has a much larger magnetic field, and so is a much more powerful like particle accelerator surrounding it. And so any time that a spacecraft needs to get close to Jupiter, it has to risk passing through this region of charged particles. And it encompasses the moons. So when you think about Io, Europa, Ganymede, Callisto, they're within the magnetosphere. And so if you stood on the surface of, say, Europa, you would experience a lethal dose of radiation in like a day. It's that bad. And spacecraft, you want to send a lander to the surface of Europa, it's going to have to deal with all of that radiation. So you would expect any planet that has a magnetosphere also has like a dangerous charged particle environment around it that is lethal unless you zip in, zip out, or figure out some way to block the particles from causing damage. Connor Campbell, rogue planets are detected by their gravitational lensing when they pass in front of a distant star. Is there any detectable effect of gravitational lensing from exoplanets transiting their own star? Right. So this idea of gravitational microlensing, this is one of the lesser known techniques that astronomers use to find exoplanets. And what they do is they watch a large portion of the sky, watching a whole bunch of stars. And when a star with a planet or like a rogue planet is passing in front of another star, you can get this natural lens where the background object is lensed by the foreground object, and it distorts the light as it passes in front. And depending on the shape of the signal, like you can get, like if you get one star in front of a star and it's just a star, then all you get is this beautiful, perfect lens as they move in front of each other. But if there's like a planet orbiting around the star, then the lensing is like not a perfect sort of lens unlens. You get this sort of anomaly on the side of the lens. And astronomers can just measure how that light changes from the background star to determine what kind of a planet, the mass of the planet that is orbiting around the star. And one of the really interesting things about gravitational microlensing is this is one of the things that amateur astronomers can get involved in. So there is a sort of an alert network. And so if you have a small telescope and you have your own ability to measure the brightness of stars, you can watch as a star is passing in front. You can receive one of these alerts, and then they ask you to jump on and make observations of that star and then send in your brightness measurements. And then you can participate in discovering exoplanets. And it's done sort of piecemeal today, but there are a couple of telescopes that are coming out shortly. One is the Nancy Grace Roman telescope, which is going to be doing this really wide scale, huge field of view, and it's going to be watching and doing very deep images of the sky. But one of the things it will do, just like as a side benefit, because it's watching all of these stars, it will be able to detect all these little gravitational microlensing events. And it's thought that the Nancy Grace Roman telescope is going to find tens of thousands of exoplanets just through gravitational microlensing. And then the other one, of course, is Vera Rubin, which is the ground-based telescope that we're all so excited about. And same thing, it's going to be taking images of the night sky every couple of nights. It's going to be noticing for anything that is changing in brightness. And one of those things that could be a change in brightness could be, say, a transit, or maybe even a gravitational microlensing event. The challenge with that is, you don't have a lot, it's not like it's continuous. And so you got to be able to do a follow-on observation, but it could very well be that it detects the presence of a planet as it's passing in front. Now, the question that you're asking specifically is that when we say do the transit method and we're looking, or the radial velocity method, and we're looking at a star and we're looking at a planet that is passing in front, does the, in addition to how the light of the planet is dimming the star, do you also get some kind of gravitational lensing effect? And my understanding is no. So I just wanted to talk about gravitational microlensing, but that was a cool question. Kaha. Due to the cost constraints, wouldn't it be cheaper to send multiple satellites to deep space at a single time versus one at a time? So this happens all the time. There is a thing called ride sharing. There are situations where you will have a rocket that is carrying some flagship mission. Maybe it's a big communication satellite or a weather satellite or something like that. But it is also carrying a whole bunch of smaller satellites on board as well. And then it will, like, as long as the smaller satellites are okay with the same trajectory as the larger satellite. If you just want to be in low Earth orbit, or you want to go to the, some Lagrange point or something like that, then you can ride share along. And often you'll have this big satellite and then packed around it are lots of little CubeSats. Also, SpaceX from time to time will actually do ride shares where they will encourage people with smaller missions, they'll gather them all together and then they'll launch, say, 50 spacecraft at the same time. Again, same constraint. You need to be okay with going to the place where the rocket is going. So if you've got some custom, like if you want to be on a polar orbit while everybody else wants to be on an equatorial orbit, then you're not going to want to be on the rideshare. And you may have to pay for the custom rocket lab launch to be able to go to the specific orbit that you want. Once you're starting to go beyond Earth orbit, though, then you run into constraints of transmission, of communication, because you're going to have to communicate far away from your spacecraft. And that often requires a larger spacecraft, something with more power, something that can generate hundreds of watts, something with a larger transmission dish that can actually be able to communicate out to, all the way from the asteroid belt back to Earth. And so that tends to require a bigger spacecraft. And then also, like the kinds of scientific payloads that you're going to want to do. Like if you're going to want a mass spectrometer, if you're going to want a laser altimeter, if you're going to want a ground penetrating radar on your spacecraft, then you're going to need to have more power. And so more power means a bigger spacecraft. And so, you're going to need a much bigger spacecraft. But there really is a revolution in miniaturization of spacecraft that has started within the last couple of decades. And we are well on our way into this new generation where you can miniaturize the propulsion system, you can miniaturize the communication system, the optics, the computers. I mean, think how small cell phone cameras are today. You can put those on spacecraft now. And so you have CubeSats, which are kind of like the size of a bread box, but there's ones that are a segment of a CubeSat, things that are like that are as big as a paperback book. And so you can imagine future satellites that are even smaller. And there are new technologies that may move away from some of these other ideas. One, for example, is being able to send your spacecraft in swarms. So instead of sending one spacecraft to do the job, why not send 100? And the 100 will communicate together and be able to work like one big spacecraft. And if there's a problem in any one of them, it doesn't really matter because they can all communicate and take over from one another. There are also other ideas where, like, say you want to communicate your data back to Earth. So what you do is you send, say, 100 spacecraft to different asteroids, and they fly out into space. They take a whole bunch of images of the asteroid that they've been tasked with, and then they fly back on their orbit, and then they transmit all their data when they get back to Earth. You don't have to worry about a big transmitter. Wait until your satellite has returned. Now it's going to take you a couple of years. You have to be patient, and you don't know if your spacecraft's okay, but it can be that you might be able to do that. And also with the Perseverance rover, NASA tested out this idea of, can we use smaller spacecraft as transmitters? So with Perseverance, they also sent 2 CubeSat scale spacecraft to Mars. And they were the ones that were doing the transmitting back home, not Perseverance. Perseverance was testing out, can I relay my communications through these CubeSats to be able to send this data back to Earth? And the test worked out really well. So we're sort of in this middle zone where, like, we can see that these big flagship missions, it's a really hard thing to justify spending $5 billion on this gigantic spacecraft. Is there a way to miniaturize the capability? Are there ways that we can use interesting orbits, new technology to be able to still get the science done, but be able to do it on a much lower budget? And the answer just keeps turning out to be more and more yes. Bug Bite, what is your personal opinion on the shape topology of the universe, observable or otherwise? As I say all the time, I'm not a scientist, I'm a journalist, so I don't have opinions about this kind of thing. But scientists think that there are different kinds of topology for the universe. Topology is like the shape, right? What is the topology of a sphere? Think about a topology of a donut. These are different sort of shapes of objects. And so there's kind of 2 possibilities about the universe. One possibility for the universe is that it is infinite, that it goes on forever. And it is really hard then to describe what is the shape of something that goes on forever. It goes on forever in all directions. And so, it's kind of hard to have a topological discussion about that. But the other possibility is that the universe is finite, that it doesn't go on forever, that it wraps in some way. And you can sort of imagine a 3D game of asteroids where you go to the side of the screen and you pop out from the other side of the screen. You go to the top of the screen, you pop out from the bottom of the screen. And then what you can't do in asteroids, you go out the front of the screen and you return in the back of the screen. And for the universe to be finite, then one of those questions that astronomers ask is, what is the topology? What is the shape of this finite universe? And can we get a sense of what it is? And so one of the questions that astronomers have asked is, can we measure the flatness of the universe? They think about like the largest possible triangles that you can imagine and make sure that the angles of the triangle add up to 180 degrees. And they find that they do, that the universe is flat. And so when you think about the possible topologies, like the universe could be a sphere, but a sphere wouldn't give you triangles that add up to 180 degrees. When you think about sort of putting a triangle at the equator of the Earth, you can have them go up to the North Pole and the angles don't add up to 180 degrees. Or you could have something where the angle is less than 180 degrees, some kind of like, is it saddle shaped? But from what they can tell, the universe is flat. And so then you've got to think about possible topologies for a finite universe that could be flat. And so I'll give you a couple of examples. Like one is a cube, right? Like if you want to travel in, if you say you send two lines, parallel lines, and they stay parallel forever, and they go along one side of a cube, and then they go over the corner of the cube, and then they stay parallel, and they keep going no matter what direction you send those lines, they're going to remain parallel. And then the best example is a torus, a donut, where if you think about a donut, same thing. You start parallel lines anywhere on a donut and they will remain parallel. You can go around the top of the donut. You can go around the edge of the donut. And that's the one, like there are other shapes, dodecahedrons, 100-sided geometric things, and all kinds of other possibilities. But I like donuts the best. So in my personal opinion, the universe is a donut, but that is not based by evidence. That it's just based by hunger. Donuts. If you want to support the work we do at Universe Today, consider joining our Patreon club. Your support lets us have a minimum of ads and no sponsorship messages. Patrons get no ads on universetoday.com for life. Want the extra parts of the live stream that are in this edited version? You can sign up for a special patron-only podcast feed and get the overtime segments as well as other special behind-the-scenes episodes, including our monthly patron-only question show. Thanks to everyone who has already subscribed, and welcome to the recent newcomers: Lee End, Exist Dissolve, Douglas Friday, Ryan, Alex Ratout, Russell Spivey, Robin A. McIntyre, Silent Phoenix, Yves Junquera, Jacob Howell, Mark Johnson, and Brian Mendoza. Join the club at patreon.com/universetoday. ASCII, what happened to the periodic methane emissions recorded by, if I recall, the Mars orbiter some time ago? So what you're referring to was periodic methane emissions that were detected by the Curiosity rover. And noticed every springtime, the methane around the rover spiked. And that led astronomers to wonder what's going on. Here on Earth, atmospheric methane is driven by a biological process, bacteria, cows. But also, we know that some amount of methane in the atmosphere can be driven by non-biotic process, volcanoes. And so the question is, which is it? And with the discovery of this atmospheric methane that appeared in the springtime when things were warming up on Mars, that feels really like an indication that there is like life is starting to use this methane. And so NASA has sent other missions to Mars, ones that have gone and actually been able to map the atmosphere of Mars. And they're still not entirely sure what the source is, but there was a paper that came out just a couple of weeks ago. Like, I haven't heard a lot on this for a while. And then just a couple of weeks ago, we got a paper that said one possible explanation is that in the springtime, as Mars warms up, it puffs out the atmosphere a bit as it's interacting with the sun. And what that can tend to do then is draw out volcanic gases from reservoirs under the ground. So if you imagine, like underneath the ground on Mars, you've got all of these volcanic chambers that are all connected together, and they're in a state of equilibrium with the overall atmospheric pressure. But as the region heats up, the atmosphere warms up, atmosphere kind of puffs out a bit, and it draws atmosphere out of the ground, which has been inundated with these volcanic gases, methane. And so that's a perfectly non-biological explanation for the discovery of methane at Mars. So I hope you're keeping track of this, right? That every time we think we've found life on Mars, it turns out that the results are inconclusive. The Viking experiment, the Allen Hills meteorite, methane on Mars, phosphine on Venus. Like, it just goes on and on and on. And I always say, be patient, buckle up. This mystery is going to take a while to resolve. David, hey Fraser, do you think that a major step in improving propulsion speed so that travel time to the outer solar system and beyond will be achieved in our lifetime? So I think there are a lot of improvements in propulsion that have already been developed that just need to be implemented. Traditionally, right, the fastest method of propulsion that we know of is a chemical rocket. Or, I mean, it's not the fastest that we know of, but it's the one that gets used. Now, ion engines have been used and they can achieve much higher speeds, but they, you can't do a lot of thrust. But as long as the ion engine can be turned on for days, weeks, months, years, it can reach enormous velocities with very efficient fuel use. And so what comes next? There's an improved version of an ion engine called a Hall effect thruster, and it's been proposed that you can attach a Hall effect thruster to, say, a fission reactor. So you generate electricity with a fission reactor. You are using that to propel ions out the back of the spacecraft, and you can achieve very high velocities. I mean, you should be able to achieve delta Vs in the tens of kilometers, maybe even 100 plus kilometer per second, which gets you out to the outer solar system within, a decade. There are proposals for fission drives, which it's expected that NASA is going to test a fission-based rocket probably in the next couple of years. They're great for transportation in between planets in the inner solar system. Like if you want to do a mission to Mars, you only want to take 90 days to get there. Then you use a fission rocket. And then there are a lot more exotic ideas. There are solar sails that you do the Oberth maneuver where you drop into the inner solar system, go past the sun, use the intense power of the sun to accelerate your solar sail, and that gets you out to high velocities out into the outer solar system. There are light sails, laser sails, where you fire a high-powered laser at a small probe with a solar sail, and you're able to accelerate it to, theoretically relativistic velocities, but even thousands of kilometers per second would be terrific. There are electric sails and magnetic sails, which interact with the solar wind coming from the sun, which theoretically can drive you up to 100 plus kilometers per second. So there are a lot of really interesting ideas that are just around the corner. And then there are the tried and true technologies that NASA and ESA and all of them have been depending on for literally decades. And it requires an investment. It requires someone to say, let's try and remove some of the risk from this technology and find out if we can make it work and be willing to invest money in it. Generally, people go for things that are tried and true as opposed to experimental technology. But every now and then, for the purpose of a mission or for the willingness to understand if we can make better technology, these really cool new propulsion systems fly. And I think that's what we're going to look at for the next, when you say in our lifetime, like those are the kinds of technologies that will probably be explored in our lifetime. And then the ones that will come after our lifetime are probably things like fusion drives. They won't get you necessarily to the nearest star, but they'll definitely give you a lot of speed here in the solar system. And then antimatter is the ultimate propulsion system, because it is the most energy dense source that you have. It's just very expensive to make antimatter at the amount that you would require to be able to travel interstellar distances. So we are, decades away from exploring some of these other technologies at scale. And then we are centuries away from the really advanced technologies, which, sucks. I'd love to see the first antimatter spacecraft set off to another star system, but I get to see pictures from the surface of planets in the solar system, and that's okay. Ernest Patriot, we can thank the gravitational effect of having Jupiter nearby, where that mass has altered the flight path of potentially deadly encounters with asteroids. People say that Jupiter is like our protector, and sure, Jupiter's got a lot of mass. It gobbles up a lot of asteroids that would have stuck around inside the solar system. But Jupiter is a bully, and it causes as much harm to Earth with its gravity as it protects us. So when you think about Jupiter and its interactions with the asteroid belt, every time Jupiter orbits around the asteroid belt, it causes these perturbations in the belt, and it kicks asteroids from the asteroid belt into orbits that bring them closer and closer to the inner solar system. And all of the near-Earth asteroids that have the potential to cause great damage on Earth are all being driven by Jupiter's gravity. Jupiter is just pushing these asteroids into the inner solar system all the time, and they are shifting and changing, and they're interacting with Jupiter more, and they're constantly ending up closer and closer, and then eventually they crash into Earth. That's what clears them up, or Earth's gravitational interaction kicks them back out again. But no, Jupiter is just like, why do you keep hitting yourself? Why do you keep hitting yourself? Because it's just constantly throwing all those asteroids. And in fact, this is one of the reasons why astronomers can't make really long-term predictions about the movements of asteroids, is because Jupiter is constantly pushing these asteroids around. It's like a train of asteroids that Jupiter is responsible for. So no, Jupiter's not your friend. Like Jupiter is at best a frenemy. Stephen Nard, please tell me if a black hole is two-dimensional or spherical. So when you sort of see the pictures, the illustrations of what a black hole looks like, you see this sort of fabric of space-time, and then there is this well, and down at the bottom is the black hole. And that's a way to sort of wrap your mind around how black holes are distorting space-time. But that is like a two-dimensional representation of an effect that's happening in 3 dimensions. The reality is that you would need to sort of recreate that weird model in all directions and in all dimensions. A black hole is a 3-dimensional object. Think of a neutron star, which is the result of a very large star that explodes as a supernova, and then the infalling material collapses down, and you end up with this rapidly rotating object that is incredibly dense and has these magnetic fields and so on. And the only thing that is stopping the neutron star from collapsing down is the pressure, the neutron pressure that stops these neutrons from being smushed into each other. But you could take the sun and you could replace it with a neutron star with the mass of the sun, which you don't get. I mean, they're generally a little bit more massive than that, but you could, if you could. All of the planets would continue to orbit around this neutron star sun, and everything would be just fine. And so if you think that a star is a 3-dimensional object, a neutron star is a 3-dimensional object. But if you feed a neutron star like one more bite that's wafer thin, one more straw to break its back, then it overcomes the pressure. The neutrons are now, they give up, they're willing to be squished together, and this thing compacts down into one more size, and that is the black hole. And now suddenly the event horizon forms around the black hole, because that is the region where now not even light can escape this thing. And so it is still a 3-dimensional object. You can orbit a black hole in any orientation in exactly the same way. So black holes, they are spherical. But like spherical is not exactly the right answer, because they rotate. They're oblate spheroids, but they are 3-dimensional objects. Intern, what is the most important resource other than water to find on the moon for a permanent human settlement on the moon? I can tell you what the next 3 most important things are to find on the moon. In fact, they're more important than water, and they are power, power, and power. Energy, energy, energy. Those are the most important things to find on the moon, and they are really the limiting factor for being able to have some kind of science station on the moon. When you think about the moon goes through this 28-day cycle where half of it, 14 days, it's in permanent sunlight. Half of it is in permanent shadow. And so you've got to spend this time where the temperature ranges between plus 150 to negative 150 or more, and it just swings back and forth. And so when you're in full sunlight, you need really good air conditioning, which is fine because you've got all that sunlight, you got all that power, that's no problem. But then when you go into the cold part, then you need a way to warm up your station so that people don't freeze. Now you can dig underground and whatever, but you're going to need, for communication and your science equipment and all of your rovers and all this kind of stuff, you're going to need a ton of energy. And that's really going to be the limiter. How much regolith can you turn into buildings? How much water can you electrolyze to be able to separate into oxygen and hydrogen? It all takes electricity. It's all going to take power. And this is one of the technologies that NASA has been investing in pretty heavily recently, which is some kind of moon-based fission reactor. And in fact, they're just in the process of going through shortlisting different ideas for fission reactors that can be used on the surface of the moon. The kinds of things that could provide, say, 1,000 to 10,000 watts of energy for 50 years. that they could send one of these things up there, they could hook it up to the station, they've got as much electricity as they need to get them through the lunar day and the lunar night and just keep going. So really that's it. It's all, once you've got electricity, once you've got power, then you can kind of do everything else that you need. But without power, you can't do anything. Kevin Kernick, how do gravitational wave detectors determine where the wave event came from? I'm understanding how they make the detection of the event, but how they determine where it originated. So when you think about the various gravitational wave detectors, we'll take LIGO for starters, that it is this facility with these long arms. They are kilometers long. And they run this laser down the arm and it bounces back and forth to form kind of like a virtual arm that is vastly longer. And so when a gravitational wave passes over the gravitational wave detector, then it changes the length of one of the arms, but not the other arm, or it changes the length of one arm more than the other, sort of depending on the angle that the gravitational wave comes through. And that makes a detection at the gravitational wave facility. But that could just be a little earthquake. It could be a truck driving past. It could be somebody setting down their coffee too hard when they're in the office. Like, these things are really, really sensitive. So they have a second facility. There's one in Eastern Washington. There's one in Louisiana, and the one in Louisiana and the one in Washington, they both have to detect the event. And so you get the wave passing one facility, and then a fraction of a second later, the wave passes the other facility. It has to have the same wavelength, has to sort of have the same properties, and that's how they know, that's how they detect and confirm that there was a gravitational wave. But when you only had the first two LIGO facilities, you had a really hard time knowing where in the sky this event was happening. So you could, like, if the wave passed one detector then the other, then it came from over there. But if the wave passed this one, then that one, then it came from over there. And so you pretty much could only narrow it down to one hemisphere of the sky. But we got a third detector with the Virgo facility in Europe. And so now you've got this equilateral triangle around the Earth. Two facilities in the US, one in Europe. And so no matter what direction the gravitational waves are coming from, you're able to determine the location in 3 dimensions in the universe and to be able to track it back. And so from this point on now, astronomers know to within a couple of degrees of the sky where the gravitational wave signal came from. And there are more gravitational wave facilities coming online. You've got the Kagra facility. There's a couple more planned. I know the Chinese are planning gravitational wave observatories. And so each one of these new observatories, as it comes online, will be able to add to the sensitivity and the location finding and the confirmation of these gravitational waves. And we talked about, I think last week, about how the European Space Agency has approved the Risa mission, which is going to be 3 gravitational wave observatories that are going to be in space. So now you've got another set of facilities that could potentially detect gravitational waves that are the same as the kind of ones that can detect on Earth, and you get more sensitivity. So it's like this growing network. The more detectors you put on Earth, the more value you get out of them. Terry Davis, is there a plan to look at stars that resemble ours with planets not tidally locked? I mean, the holy grail of exoplanet hunting is to find an Earth-sized world orbiting around a sun-like star in the habitable zone. But the problem is that for us to be able to detect the presence of that planet, you're going to need a very powerful telescope that is able to block the light from the star to be able to look at the planets themselves. So far, like just using, say, the transit method, astronomers have not found any planets that are like the Earth and the Sun. And when you look at the kinds of planets that they have found, that tells you sort of what the problem is. So what they found is Earth-sized worlds orbiting in the habitable zone of red dwarf stars. And in this case, because it's in the habitable zone, it is much closer to the star and it's orbiting a lot more quickly. It might take only a couple of weeks to go around the star. And so you get confirmation. And so you know that your planet is there. They've detected hot Jupiters that, again, you've got a planet that is going around its star. It could be a sun-like star and the planet is only taking 3 days to go around its star. And so you get confirmation. But when you think about what's going to happen for us to be able to detect Earth, you need to be watching a sun-like star. You need to watch as an Earth-like planet passes in front of it. You have to know to watch again in 365 days, or just like not look at anything else. Just watch that one star, wait for that planet to come back 360, but you don't know how long it's going to take. It could take 1,000 days. It could take 7 days. You don't know. And then you have to wait another 365 days to get another confirmation as it passes in front of the star. So like the bare minimum, you need 2 years of continuous observations. And the Kepler spacecraft, which unfortunately died, this was the plan, was they took this spacecraft, they were going to stare at this gigantic field of the sky for months at a time. And the hope was that it would be able to detect that very rare transit of an Earth-sized world orbiting around a sun-like star. But unfortunately, the reaction wheels on the Kepler mission failed, and so it wasn't able to hold its position. And so they had to come up with a different strategy. They used it for looking at red dwarfs. They weren't able to use sort of its full, complete plan. And there hasn't been a replacement. There's TESS, but TESS isn't exactly up to this. So right now, there are no missions in the works to try to redo what Kepler was going to try to do. And I think that's a problem. And I'm sure the astronomical community is aware of it, and they've got a plan for this. But I've interviewed tons and tons of people, and I haven't found anyone that's given me a really satisfactory answer. Like, what is Kepler died. It didn't do its primary mission. It wasn't able to find that Earth-sized world orbiting around a sun-like star. People are planning the Habitable Worlds Observatory, which is going to be this telescope capable of observing an Earth-sized world orbiting around a sun-like star. But there isn't a lot of space satellites that are in the pipeline to do the finding, to find all of the candidate exoplanets first, so that then you can actually know to do your follow-on observations. Now, there's a telescope that I really like called Life, and it sort of has two modes. One is, it's an interferometer, which, I love. And one possible version of it is that you would be observing individual exoplanets and try to, orbiting around sun-like stars and try to look at the planets. But if you don't have candidates, then you can look at lots of other planets and try to identify new candidates. And so I think if there's like one telescope that I would love to see move forward, like if I had to choose between the Habitable Worlds Observatory and Life, I would probably choose Life. It's an interferometer. It uses nulling to provide its coronagraph. I've done an interview with the principal investigator on it, and I think that's the space telescope that I'm most excited about. So no, there isn't a great plan right now to be able to see those Earth-sized worlds. There's like, let's make the powerful telescope that can observe them in the 2040s. And there's like, let's use TESS to find all of the nearby exoplanets. But there's in the middle, this sort of question mark, when we need to find thousands of candidate Earth analogs that then can be observed by the Habitable Worlds Observatory. And right now that just doesn't exist. We have not found one single Earth-sized world orbiting a sun-like star in the habitable zone. We have not found Earth 2.0 yet. All right, those are all the questions that we had this week. Thank you, everyone, for asking the questions in the YouTube comments. And thank you to everybody who joined us for the live show. Now, we do the show every Monday at 5 p.m. Pacific time. So if you want to join in the show, it is like twice as long as the episode that you're watching right now, with questions, follow-on questions, overtime. It's a lot of fun. Monday, 5 p.m. I'll put an event here on the channel for the next one, and you can figure out a way to remind yourself to join that show. I'm going to talk about smaller, good space YouTube channels in a second. But first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrew Gross, Antonio Lofilara, David Giltonen, Dougie Stewart, Dustin Cable, George, Jeremy Mattern, Jordan Young, Josh Schultz, Mark Anstis, Paul Rohrbach, Stephen Krasaki, and Vlad Shiplin, who support us at the Master of the Universe level, and all of our other patrons. All your support means the universe to us. So in the last question show, I got a question from someone which was like, who, with all of the low grade spam content here on YouTube, that it's hard to know what is real and what is not, and who can you trust and who can't you trust, people wanted some of my recommendations. And I went through all of the big heavy hitters who you're all very familiar with. Many show up on my channel all the time. And it sort of made me think, like, there's so many great smaller creators, people who are in the under 10,000 subscribers on YouTube who are doing an amazing job of communicating, and they're just not getting enough support. And I want to try and use my channel to be able to drive as much support for these other channels as I can. And so I know a bunch of these channels, and I will recommend a bunch at you in the coming weeks, but I would love for you to tell me, like, what are some channels that I should go and take a look at? Put them in the comments down below. I will go and check out their channels, and, you know, if they meet my criteria of like science, you know, if they're saying good things, you know, they're saying proper science, I will sort of gather a bunch of those up, and I will try to highlight a few each week for the next, I don't know, for as long as it takes for me to run out of channels, which might be forever. I don't know. So, but I want to sort of start this ball rolling. And that is, I did an interview about a week ago with Dakotah Tyler, who is a doctoral student at the University of California, Los Angeles. And he was the researcher who's working on this planet with a comet-like tail. And he had been on the weekly space hangout for a couple of weeks as well before we shut that down. But I didn't realize that Dakotah's got his own YouTube channel, and he's got his own TikTok, and he's got his own Twitter, and he does a ton of really interesting videos sort of from his perspective as an exoplanetary scientist, but also with, you know, some of the more other topics that he looks into. And so I wanted to point you towards his channel this week, which I sort of didn't realize how active he was across all the social medias. So that's Dakotah Tyler. His sort of handle is Star Kid, which I think is awesome. So definitely check out his channel, and then give me recommendations for channels of other people here on YouTube or even across other social media who don't have big followings, who you think are underrated, who could get more fans so we can help get more positive voices in space science. All right, we'll see you next week.